Finally, we'll demonstrate how to use Bus Expert 2 in real-world applications to help you better understand its capabilities in various measurement scenarios. These examples will cover measurement cases in both logic analysis mode and protocol analysis mode, focusing on how B2 can be used to test eMMC and SD bus signals. Through these examples, we'll show you how B2 enhances debugging and analysis abilities, ultimately boosting product development efficiency. First, let's go over how to correctly set up the B2 hardware environment to ensure measurement accuracy and reliability. Following these steps will help you prepare an optimal hardware setup before starting your tests. To achieve accurate measurements, it's essential to configure the necessary hardware. This includes selecting the appropriate test device, setting up the test environment, and confirming that all components are functioning properly. We'll be using a high-speed SD 3.0 card or eMMC as our DUT. These storage devices are widely used in mobile devices and embedded systems, where stable signals and accurate decoding are crucial for proper measurement. Ensure you're using a high-speed card reader capable of supporting at least a 104 MHz operating frequency to handle the DUT's maximum frequency during measurement. Before measuring, it's critical to calibrate the probes. This step is essential for accuracy, ensuring that the results are not impacted by environmental or equipment issues. When connecting the probes to the measurement system, ensure they're positioned and contacting correctly. Improper calibration can lead to signal deviations or inaccurate measurements, so it's essential to calibrate the probes before each test. Now, we'll connect the probes to the DUT to begin capturing and analyzing signals. Make sure the probes have a secure connection with the DUT, whether it's an eMMC or SD card. Unstable signals can impact results, so confirm that the contact points are solid. Important notes: during connection, ensure there's no loose contact, and that the power supply is stable. These factors are directly linked to measurement accuracy and result reliability. Once the hardware setup is complete, perform a simple test to verify that everything is functioning correctly. A quick signal measurement can confirm that the probes, card reader, and DUT are all properly connected and working. Once you observe a stable signal waveform, you're ready to proceed with detailed measurements and analysis. Connect the clock signal to channel A0. This will help you synchronize the analysis of subsequent signals. The clock signal is the foundation for most protocol analyses because it dictates the timing for data transmission and reception. Connect the command line to channel A1. Command is the main signal for control instructions, used to manage the transmission of protocol commands. In many memory protocols, the command line is used to send read, write, and other operational commands. Connect the data lines, D0, D1, D2, D3, etc., to channels A2, A3, and so on. These data lines carry the actual data or command parameters, making them one of the most important signals in the protocol. In this section, we'll introduce the LA mode application of B2 and use CMD6 command analysis as an example to show how to test and analyze the CMD6 command with a logic analyzer. CMD6 is a command in the SD card protocol used to set or test the card mode switch, which is essential for evaluating card performance in different modes. Let's start by understanding the basic function of CMD6. CMD6 is a mode switching command in the SD card protocol, allowing users to control the card's operating mode, selecting between different performance modes, such as normal or specialized modes. This is crucial for testing how the card performs under various operating conditions. Typically, this command is used to switch the card's functional mode, such as activating high-performance data transfer or entering standby mode. CMD6 is a frequently used command for these types of adjustments. In B2's LA mode, we can set trigger conditions to capture the CMD6 command, helping us accurately capture and analyze the transmission process of this command. First, you'll need to configure the event trigger condition on B2. In the B2 interface, click on the Options menu at the top, then choose Event Trigger from the drop-down. Select CMD Sequence Trigger, and set the trigger condition to CMD6. This will enable the system to automatically capture data around the CMD6 command. Once set, B2 will begin capturing and displaying detailed data related to this command whenever CMD6 occurs. Next, you can define the number of times the trigger will activate, which allows you to control how many times B2 records the CMD6 command's transmission. You can set it to single trigger, meaning B2 will stop capturing after detecting CMD6 once, or select multiple triggers, where the system will continue capturing each time CMD6 is detected until the trigger count is reached. Multiple triggers are often helpful for troubleshooting or performance testing since they allow you to capture multiple instances of CMD6, giving insight into how the card responds under various conditions. To complete this setup, click on the sample menu at the top. From the drop-down, select Advanced Trigger Settings and enter the desired trigger count. The setup is now complete. In this section, we'll dive into using Bus Expert 2, B2, for CMD6 command analysis and examine the associated signal timing transitions. For accurate CMD6 command analysis, setting the right trigger is essential to ensure precise data capture. Start by clicking the Options menu at the top. From the drop-down, select Event Trigger. Check the CMD Sequence Trigger option, and set the trigger condition to CMD6. Then, go to the Sample menu at the top, and in the drop-down, select Advanced Trigger Settings. For trigger count, enter 2 to complete the setup. Examining clock transitions of the device under test. When analyzing the CMD6 command, we need to focus first on the clock transitions of the device under test. The operation of an SD card or eMMC device can be affected by clock frequency changes, particularly during certain commands like CMD6. During CMD6 execution, the clock might shift from a low to a high speed, which significantly impacts the subsequent data transfer. Before CMD6 execution, the device under test typically operates at a 25 MHz clock frequency. This frequency is the standard operational clock for SD cards or eMMC in normal mode, and all data transfers and signal processing occur at this lower frequency. Using B2, we can observe the clock's stability and signal shape at this stage, which helps ensure stable device performance early in operation. At this stage, the signal is stable with minimal fluctuation. After executing CMD6, the device clock shifts from 25 MHz to 100 MHz, more precisely, 104 MHz. This change happens because CMD6 is used to switch the card's operational mode to support faster data transfer. At this higher frequency, the data transfer rate improves, enhancing system performance. Using B2, we can precisely capture the transition from 25 MHz to 100 MHz, typically accompanied by increased signal frequency and shape changes. We will examine waveform stability and verify clock signal integrity. If the waveform shows abnormalities like jitter or instability after the transition, it could indicate an error in the mode switching process, requiring further configuration checks or adjustments. To ensure the clock transition post CMD6 is correct, we need to perform the following checks in B2. Clock frequency stability check. During the shift from 25 MHz to 100 MHz, the clock frequency must be stable and meet expectations. Any instability could compromise data transmission reliability. Signal shape check. After the clock transition, the signal shape should remain clear, without excessive noise or anomalies, ensuring data transfer in high-speed mode is free from interference. Comparing pre- and post-trigger signal changes. Using trigger settings, we can capture each detail during the clock transition and compare signal characteristics before and after to identify potential issues. By using B2 for CMD6 command analysis, we gain insights into clock transitions during command execution. The shift from 25 MHz to 100 MHz is crucial to ensure the card supports high-speed data transfer. Through precise clock checks and signal analysis, we can quickly detect issues, ensuring test reliability and ultimately enhancing overall system performance and stability. In this section, we'll focus on data packet analysis for CMD 17/18 and CMD 24/25. These commands are common read and write instructions for storage devices like SD cards or eMMC. We'll use the Bus Expert 2, B2, to capture and analyze these data packets to ensure that each command executes accurately. CMD17 is a single block read command, used to read one block of data from a storage device. This is a common operation, especially in applications that need to handle small amounts of data. CMD24, on the other hand, is a single block write command, which writes data to a single block on the storage device. CMD18 is a multi-block read command, meaning it can read multiple data blocks from the storage device in one go. CMD25 is a multi-block write command, used for writing data to multiple blocks at once. Setting the bus trigger for CMD18. Click on the Options menu at the top. From the drop-down, select Event Trigger. Check CMD Sequence Trigger and set the trigger condition to CMD18. Next, click on the Sampling menu at the top. In the drop-down, select Advanced Trigger Settings. Enter 1 as the trigger count to complete the setup. Data Packet Observation, confirming packet format and data integrity. Observing data packet format. When executing CMD17 and CMD18 commands, data is packaged in a specific format. These packets usually contain a command header, data block, and a checksum, such as CRC. Using B2, you can easily capture and observe the detailed content of data packets, ensuring the format is correct and that the data matches expected values. During this process, you can examine each block's header, command, and data content to confirm they fully comply with protocol requirements. The visual tools in B2 allow you to quickly check the integrity of data packets. You can verify if any packets are missing, have errors, or contain abnormal data bits, ensuring that data isn't damaged or lost during the read/write process. During data transfers with CMD17 and CMD18, cyclic redundancy check codes are used to detect errors in transmission. If a CRC check fails, it indicates a possible transmission error. B2 supports automatic CRC checking, allowing you to quickly verify if each packet's CRC matches. When errors occur, the system flags the problematic packet, helping you quickly locate the issue. This feature allows you to identify and fix errors early, improving testing accuracy. In this case, the command line may be affected by noise or external interference, causing measurement errors. The data signal may also show similar noise. If you notice issues in data packet analysis or unstable signals, it's essential to check the grounding of both the probe and the device under test. Ensuring good grounding is one of the most effective ways to address signal interference. Enhanced grounding reduces electromagnetic interference on the signal, improving measurement accuracy. In this section, we'll look at the application of CRC checking in Bus Expert 2 and how we can use this feature to ensure data packet integrity and reliability. CRC, or Cyclic Redundancy Check, is a common error detection code that helps verify if data has been corrupted during transmission. In many communication protocols, transmission errors are inevitable. CRC checks are typically used to make sure data isn't altered or damaged during transmission. B2 has a powerful CRC check feature that automatically verifies each received data packet to see if it matches the expected CRC value. This ensures that the data you capture is complete and unaltered, so any analysis results are accurate and error-free. When B2 analyzes data packets, it automatically calculates the CRC for each packet and compares it with the CRC embedded in the packet itself. This allows users to quickly assess if errors occurred during transmission without the need for manual CRC calculations. Automatic comparisons significantly speed up detection and enhance accuracy, allowing users to analyze efficiently. If B2 detects a discrepancy between the calculated CRC and the expected value in a packet, it can trigger an error alert and immediately flag the erroneous packet. This real-time feedback lets users quickly identify which part of the data has an issue and make necessary adjustments. This feature is essential for quickly pinpointing transmission errors and allows immediate corrections during testing, minimizing the time needed for manual error checks. To set this up, click the Options menu at the top. From the drop-down menu, select Event Trigger, then check both Write CRC Error and Read CRC Error. By leveraging the CRC check function, you can ensure data transmission reliability and pinpoint suspected errors accurately. If a CRC error is detected, the system provides immediate feedback, helping you locate the problematic data block quickly. This improves measurement accuracy and assists developers in identifying potential issues early, ensuring stable and reliable device operation. This technology is invaluable in product development and debugging, especially during complex data communication testing or validation. The CRC check function in B2 is a vital tool that helps users automatically calculate and compare the CRC values of each data packet, effectively verifying data transmission integrity. When CRC errors are detected, the system triggers an instant error alert, helping you quickly locate and correct the error to ensure reliable data transmission. This feature is essential for precise debugging, improving system stability, and enhancing testing efficiency and data analysis accuracy. Here, we have an example of how clock interference can lead to CRC errors, where you can see a slight spike on the CLK signal. During data transmission, the clock signal is crucial for maintaining data synchronization and accurate transfer. If the clock signal is interfered with, it can lead to transmission errors and cause CRC check failures. Here are some possible scenarios. Clock signal distortion: when the clock signal is affected by external interference sources, like electromagnetic interference, the clock waveform can become distorted, causing timing misalignment in data transmission. This misalignment affects data decoding on the receiving end, leading to CRC errors. Unstable clock source: if the clock source itself is unstable or fluctuating, each clock cycle in the transmission may be inaccurate, resulting in bit errors and failed CRC checks. Data errors due to clock interference: when the clock signal is disrupted, each bit in a data packet may be decoded incorrectly, generating an incorrect CRC value. Such errors are difficult to identify directly, so it's essential to check clock stability and signal quality. Summary of steps to address CRC errors. Check the waveform display to confirm the stability of the clock signal. Add shielding, grounding, or filtering measures to reduce external interference. Verify the quality of the clock source to ensure it remains stable. Calibrate probes properly to guarantee accurate signal measurement. When encountering CRC errors, the first step is to investigate whether clock interference could be the cause. Using B2's clock signal observation feature, we can promptly identify and address any instability or interference issues with the clock, ensuring data transmission accuracy and integrity. When handled correctly, these errors can be detected and resolved quickly, improving data analysis reliability and testing efficiency. In this section, we'll take a deep dive into how to use Bus Expert 2, B2, for CRC checking, with a special focus on how to quickly identify and handle CRC errors when data is disrupted. CRC, Cyclic Redundancy Check, is a common error detection mechanism used to ensure data is not corrupted during transmission. When data interference occurs during transmission, CRC errors quickly become apparent. Now, let's go over how to identify these errors and explain the signs of data interference. How to identify CRC errors caused by data interference. In B2's LA mode, we can detect if data is being interfered with and causing CRC errors by following these steps. Observe the waveform. In B2, the data waveform clearly shows the quality and stability of the signal. If the waveform displays abnormal disturbances, it could indicate that the data is being interfered with. In such cases, CRC checking will show an error. Here, we have two examples of data interference affecting CRC errors, where you can see small spikes on the data signal. Check the CRC of the error packets. When a CRC error occurs, B2 will mark the error packets and display the erroneous CRC values. Users can inspect these packets and compare their data content to confirm if data interference is the cause. Check the stability of data transmission. Data should be transmitted at a steady interval. If there are sudden delays or packet losses, it often points to interference causing signal issues, which in turn leads to CRC errors. By using these steps in B2, you can quickly identify and analyze CRC errors resulting from data interference and take action to resolve them. This image shows the situation after taking measures such as checking the waveform display to confirm if the clock signal is stable, adding shielding, grounding, or filtering to reduce external interference, checking the quality of the clock source to ensure its stability, performing proper probe calibration to ensure accurate signal measurements. After implementing these steps, we are now able to measure the correct data CRC status. In this section, we will discuss how to effectively troubleshoot and handle CRC errors. By using the right troubleshooting strategies, we can quickly identify and resolve the root causes of CRC errors, which will improve system stability and data reliability. Below are some common strategies that can help you effectively address CRC errors. When a CRC error is detected, the first thing to consider is using software filtering to reduce unnecessary noise and interference. These filtering options can help filter out irrelevant interfering signals and focus on valid data packets. Filter settings. In the B2 software interface, we can set filtering conditions to eliminate unwanted noise or abnormal data packets. Filtering helps reduce the impact of interference during the data analysis process, improving the accuracy of data decoding. Proper filter parameters. Choose suitable filter parameters to adjust for specific error patterns. If the signal quality is poor, you can increase the filtering strength to remove high-frequency noise. Click the Analysis menu above, then select Noise Filtering Settings. Choose the channels that need filtering and set the filter duration. Signal grounding and shielding are critical to ensuring high-quality data transmission. If CRC errors are found in your test environment, check the probe grounding and signal shielding for any issues. Here are a few actions you can take. Enhance grounding. Ensure there is a good ground connection between the test equipment, PCBA board, and probes. Poor grounding can lead to signal fluctuations, increasing the likelihood of data errors. Signal shielding. Signal wires should have proper shielding to prevent external noise interference. Especially with high-speed signal transmission, improper shielding can severely affect signal stability. Reduce probe-induced noise. Ensure the connection between the probe and the device under test is as short as possible, and use specialized shielded cables to avoid electromagnetic interference. Reduce long-distance transmission. When transmitting data, minimize the length of signal wires to reduce signal attenuation and reflection during transmission. If long-distance transmission is necessary, use appropriate signal amplifiers. If CRC errors persist and cannot be resolved, you can use an oscilloscope to check the quality of the signal waveform. An oscilloscope provides more detailed signal waveforms, helping us more accurately identify issues with clock, amplitude, and noise. Check clock waveform. If the clock signal is unstable or distorted, it will affect proper data decoding. Use the oscilloscope to check for abrupt changes or attenuation in the clock signal. Observe data waveform. If the data waveform shows discontinuities or disturbances, it could be caused by interference or reflections. Detect noise sources. The oscilloscope can help detect noise in higher frequency ranges and determine whether the noise originates from the device or external environment. When facing CRC errors, PCB trace routing and impedance matching are also important factors to consider. The design of transmission lines has a significant impact on data integrity, especially with high-speed signal transmission. Trace design. Check the routing of signal lines on the PCB, and try to avoid long traces to reduce signal attenuation or reflection during transmission. Impedance matching. For high-speed signal transmission, the impedance of signal lines must match the impedance of the device ports. If the impedance is mismatched, signal reflection occurs, leading to data errors or distortion. Reduce crosstalk. Check for crosstalk between different signal lines and maintain sufficient spacing between signal lines to avoid signal interference. 5. Adjusting IC drive capability and delay. The drive capability and delay of ICs are also key factors influencing data transmission stability. If certain ICs cannot drive signals adequately or have too much delay, data distortion may occur during transmission, leading to CRC errors. Adjust drive capability. Ensure that the ICs driving the signals have sufficient current strength to effectively drive long signal lines or external devices, preventing signal attenuation. Reduce delay. During the design phase, try to avoid introducing unnecessary delays during signal transmission. Excessive delays will make data synchronization issues more prominent, leading to data errors. When facing CRC errors, Bus Expert 2 provides a set of effective strategies, covering both software filtering settings and hardware adjustments to ensure data transmission integrity. We can effectively address CRC errors and ensure data reliability and transmission accuracy by improving grounding, enhancing signal shielding, using oscilloscopes to check waveforms, adjusting trace routing and impedance design, and optimizing IC drive capabilities. This slide shows how, after using the signal filtering function, some of the 16 Costa Rican colonase data packets were corrected from their original erroneous values back to the normal values. In this section, we'll discuss the application of PA mode during the boot process, focusing on verifying the stability and correctness of the boot process. Here are the steps and key points for performing boot timing tests using Bus Expert 2. Detecting signal behavior during boot in any system's boot process. Proper signal behavior is critical. This is because the signals involved in the boot process not only deal with hardware initialization but may also include many key data transfers and device configurations. Checking protocol compliance during boot. During the boot process, the boot protocol dictates the order in which commands are sent and received. Here, we need to ensure that every protocol interaction during the boot process is in compliance with the specifications. Protocol decoding and analysis. Use B2's protocol analysis feature to decode and examine the data interactions during the boot process, ensuring that each protocol communication follows the correct sequence. B2 supports decoding and detection of multiple protocols, allowing quick checks for any violations or abnormal data in the protocol. The stability and correctness of the boot process are fundamental to ensuring that the system runs smoothly. Through in-depth analysis of various signals and protocols during the boot process, we can quickly identify potential issues and take corrective measures. Timing stability check. For the timing during boot, we need to ensure the stability of each signal, whether it's the clock signal or data line signals. Any abnormalities or deviations in timing could prevent the system from booting correctly or cause other errors. B2 provides precise timing waveform displays for each signal, making it easy to spot such issues. Protocol consistency check. In addition to timing, the consistency of protocols during boot must be ensured. Each boot step needs to follow the respective protocol standard to ensure correct data transmission in a stable system boot. Error localization and debugging. If the system fails to boot properly, using B2 for error localization becomes very straightforward. You can accurately pinpoint the issues in the boot process based on timing diagrams and protocol analysis, whether it's a hardware issue or a protocol-related error. This helps catch issues early, reducing debugging time and costs. Conclusion. In summary, boot timing tests are a crucial part of the boot process. With the powerful features of Bus Expert 2, we can deeply analyze the boot signals, protocol flows, and check the stability and correctness of the boot process. This not only helps us validate the system's boot procedure but also allows us to quickly locate and resolve potential issues, ensuring the system can boot and run smoothly. Choose the SD 3.0 PA mode and set the sample depth to 50 MB. Make sure to enable options for recording read data packets, write data packets, and packet lengths. Double-check the trigger level and make sure the probe is properly connected. Press the Start Record button, then connect the device under test to the computer. Once the computer recognizes the SD card, press the Stop button. Now we can easily see the SD card boot process flow. In this section, we'll explore the application of PA mode in data packet analysis during the file copy process. File copying is a common and important operation in data transmission, especially when dealing with large-scale data movements or storage devices. With Bus Expert 2, we can closely observe and analyze the behavior of data packets during the file copy process, helping you identify issues and improve the reliability of file transfers. During the file copy process, data is transferred in the form of packets, each containing multiple key pieces of information. Using B2, we can track each packet's transmission process and perform detailed signal analysis on each packet. Packet tracking goals: by tracking packets, you can clearly understand the status of each data packet throughout the transmission process, from the start to the end, including the packet's beginning, data transmission, error detection, etc. This tracking helps you understand the flow of data and detect potential abnormalities early. Signal observation: B2 provides powerful signal observation capabilities, allowing you to see the transmission status of every data packet during the file copy process, even down to the individual bit level, helping you catch any small anomalies. Ensuring correct packet transmission. Packet integrity is key to ensuring data is not lost or corrupted during transmission. In file copying, any packet loss or error could result in data inconsistency or transmission failure. With B2, we can perform integrity checks on data packets to ensure accurate transmission. Integrity checking method: B2 offers features like cyclic redundancy check to automatically check error codes for each packet and compare them. If any packet errors are detected during transmission, B2 will immediately alert you and show the exact location of the error. Packet structure analysis: in addition to CRC, B2 also supports checking the structure of packets to ensure the data inside the packet is not tampered with and that the logical structure between different data segments is correct. This is crucial for high-demand data transmissions. Real-time detection of abnormal data: identifying packet transmission errors during file copying. Any abnormal data transmission will affect the final file result. Whether it's due to hardware issues, interference, or protocol errors, abnormal data will cause the file copy process to fail. Therefore, real-time detection of abnormal data is an important part of file transfer analysis. Abnormal detection feature: using B2's abnormal detection feature, you can set specific trigger conditions to capture errors or anomalies in data packets. These anomalies could include CRC errors, bit errors, data loss, etc. B2 will immediately alert you, helping you quickly locate the problem. Improving file transfer analysis accuracy for fast issue localization. Accuracy improvement: B2 provides high-precision timing analysis and packet parsing capabilities, allowing for extremely accurate tracking of the transmission process of each packet. This ensures transmission accuracy. Whether it's low-speed or high-speed data transfer, B2 can provide precise analysis, helping you quickly identify and resolve issues. Issue localization: if problems occur during file copying, B2 can help you pinpoint the exact location of the error and clearly display the related packet content and error information. This allows you to quickly locate the source of the problem. Such analysis greatly improves problem-solving efficiency, especially during large-scale file copying or transfer operations. Conclusion: in summary, the application of PA mode in file copy data packet analysis allows us to precisely detect and analyze the data transmission process. Through packet tracking, integrity checks, abnormal data detection, and high-precision problem localization, we can quickly ensure the accuracy and stability of file copying and promptly address any issues that arise. By using Bus Expert 2, B2, you can significantly improve the reliability of file transfers and further enhance work efficiency. The following is an example of correctly transmitting multiple blocks of data. Choose the SD 3.0 PA mode and set the sample depth to 50 MB. Make sure to enable options for recording read data packets, write data packets, and packet lengths. Double-check the trigger level and make sure the probe is properly connected. Hit the Start Record button, then copy a file from the SD card to the computer, or from the computer to the SD card. Once the file copy is complete, press the Stop button. Now we can easily analyze the SD card's file copy process.
Thank you for watching.